was work done on my master's about 2 year and a bit ago now. So this was basically the final presentation for the master's to finish up at Stellenbosch. So we're looking at unlocking the potential of harvest onboard computer data in the South African forestry value chain. So during the last probably 10 years more, there's been an increased shift towards more fully mechanized systems in South Africa, and this is mainly driven by health and safety concerns related to chainsaw operations, and then also armed systems productivity and product quality. These modern machines are extremely powerful tools on the back end, on the computer side of things, with very detailed software. Most of them, or basically all of them, run on the standard for forest communications called Stanford D, which is like a baseline data type, which collects vast amount of tree data, sizes, lengths, productivity data, machine uptime, fuel consumption, engine runtime, basically everything. So this provides a standardized platform through which almost every function and action of the machine can be monitored. And as I said, provides very detailed tree and productivity data. So I mean, from this, you get feedback from the harvester as to what's been felled. It essentially is able to get geotag, which you then know in a certain rack in the compartment, the forwarder can go pick up the volume the harvester put down. That can be pulled, so you know exactly what the forwarder did, and then where that timber gets put on depot, and then what gets sent to mill. So from the fully mechanized system, you can run a fairly smooth operation with harvesting data. The only thing in South Africa is that the software and the ability to utilize it comes at quite a bit of a premium, as the technology is European, and the rand euro doesn't always favor us. So in the South African forestry context, most machines are compatible with the Stanford D systems. As I said, the essential usefulness of the concept is underutilized due to a limited understanding between the interface between the harvesting heads and the computing systems. One of the problems is the calibration of the harvester head with regards to length and diameter measurements, and then also with regards to bark functions, and then obviously volume calculations that goes with that. So this leads to poor quality data, which can't really use for management purposes as it's not reliable. And on top of that, you're losing a lot of value because you're not using the machines to their fullest capabilities with software that is readily available on the majority of the brand new purpose-built machines. So the objectives of this study was to propose and develop an applicable bark deduction method for Pinus spatula in the Mpumalanga Highveld to get more precise underbark log volume calculations. So based on the objective, we also looked at the impact of bark deduction method, calibration or non-calibration on the harvester's log diameter calculations, the log length measurement accuracy, and then also what influence the actual stump height as versus what the machine's computer thinks the stump height is, and the data that you get for DBH measurements from the machine to versus actual measurements. So the study was done in Warburton on Jesseville Plantation. It was a nice 20-year-old stand, 0.9 cubic meter, so nice, good-sized pine, flat compartment, no issues there, with a nice slope. Machine is a nice big Ponzi Bear 8-wheeled harvester, big machine, the Ponzi H8 harvesting head, big head, no size with it, no problem with tree size, and then running on the Ponzi Opti 4G computer system, which, yeah, I mean, that's basically Windows on the harvester. So it all started with needing to get bark thickness data. So we used data that was collected during Hans Kortz's master's thesis at Stellenbosch. We used that and modeled that data we got from that to get the inputs for the machine. With that data, we parameterized the Stanford D bark deduction methods that is available on the harvester. An issue with the bark deduction methods is that the majority, because the machines are generally always from Scandinavia, there's no inputs readily available for South African conditions. So we needed to work within the framework available on the system in that. So we tested two bark deduction methods. The one was a length-based bark deduction method, the other one being a diameter class length-based bark deduction method. We'll get into a bit more detail a bit later on. So we tested these bark deduction methods. So we conducted 3 trials of 40 trees each. In trial 1, we harvested 40 trees with no bark deduction method. So that is the control with the as-is status quo operation. Then trial 2 tested the length-based bark deduction method, and trial 3 the diameter class length-based bark deduction method. Then we analyzed the 2 bark deduction methods against the control, looking at or comparing the harvester's log small end and large end diameters versus a manually measured control. And then also looking at log length measurement accuracy, basically just what the harvester measures and what compared to a manual measurement. And then also looking at the underbark volumes and how that was influenced by the bark deduction methods. So the bark data set, we took from Hans Kortz's data, we took data specifically for the Mpumalanga region with trees in the age class of 18 to 32. So we modeled that. So you can just see in total we had 117 trees, and then that was split into the different groups based on diameter for that specific diameter class, as we've seen that bark thickness is influenced by tree size as well as a range of other factors, but that was mainly on which what we went here. So the harvesting procedure, 3 trials, 40 trees each. After each trial, the Stanford D-stem files was pulled from the machine's computer, and that data was then compared to the manual measurements for each log. Manual measurements was taken log length and log end diameters. Log length was measured with the logoscope, and then we used some clever photogrammetry by taking a photo of each log end that was calibrated with the ruler. We then did photogrammetry analysis through ImageJ on a computer to get very detailed length measurements. On the analysis side of things, we compared the log large end and small end diameters, log length and log volume. So basically, we just calculated the measurement error. So you took the manual control measurement and then subtracted the harvester's measurement, and then we analyzed that difference from through 0. So on the methodology side and the research design, 3x4 factorial. So factor A was the bark deduction methods. Trial 1, no bark deduction. So the control, then T2 length-based, and T3 diameter class length-based. Factor B was then the log assortments that we got. So we were cutting long saw logs, plywood, U-saw, and pulpwood. Yeah. Modeling the bark thickness, as you can see, this graph shows in percentage terms of tree length, the thickness of Pinus spatulus bark. So you can see for the first 10% of the tree, the bark thickness varies from 10 centimeters to about 4 centimeters. So for that first 6 or so meters, 2 to 3 meters, you get an extremely thick bark, which then tapers off fairly quickly and then remains constant from there, ranging between 1 and 2 centimeters in thickness. And this is this thick bark initially that causes the issues. As you can imagine, if the harvester overbark measures the overbark diameter, uses that for volume calculations, we'll get quite a bit of an overestimation in bark thickness. So for the length-based bark deduction, we split the table into these length classes. So from the base of the tree to 2 meters, the bark input was 63 millimeters, and then from 2 meters to 4 meters, 27 millimeters in thickness, and so on. So that was a set parameter on the machine's computer for the specific bark deduction method. On the diameter class length-based, it was exactly the same, just you had an added length class based on dBH. So for specific dBH tree size, there would be a bark deduction or bark thickness allocated to that dBH class, and then on the position of the tree from the base where that bark was. So looking at some of the results we got, so the blue shows treatment 1, which is no control, is the control. So what this shows is how much more accurate the large end diameter was with a bark deduction method. So for long saw logs, on the large end of the log, we were missing a mark by about 1.4 centimeters. So that's the difference between what the manual log diameter measurement was, and then as to what the harvester's computer said the large end diameter was. And then as you can see, with each of the treatments with the bark deduction methods, we got this quite a bit closer to 0, which then means we are getting a more accurate estimation of large end diameters. On the small end diameters, the same trend was there, although the results was a bit varied, but in essence, it still stays the same, that especially on the long saw logs, we did get a much more accurate diameter estimation with the bark deduction methods, although there was some results that didn't differ significantly. The big other one was on the plywood logs, which was generally the first few logs cut from each tree. So that would be logs cut from the area with the thickest bark, where we also improved the harvester's log diameter estimation. So this is just a quick show. So on average, so to get a better understanding of the log diameter estimation across that area of the tree where bark is thickest and changes rapidly, that 0 to 4-5 meters, we pulled the data for the plywood logs cut, as those were the logs cut on the lower part of the tree. So this shows that the position of the cut, so that would be average stump height is 0.17, and then so that's the first cut. So on that 0.17 centimeters from the base of the tree, the manual measurement of the diameter under bark was 35.5 centimeters compared to what the harvester was measuring at 42.89. And for trial 1, that harvester measurement is obviously over bark. And as you can see with treatment 2, with the length-based bark deduction method, the manual measurement was 34 centimeters, and the harvester's measurement with the bark deduction method was 34.29. And then same with the diameter class length-based bark deduction method. First measurement manually 39.72, and then the harvester's measurement improved to 39.65. So that's from a first measurement difference of about 21% between the manual under bark measurement and to what the harvester's computer says with no bark deduction. That difference improved to 1.6 and 0.2. And as you can think, because that difference is so big there, that plays a big factor in the volume calculation that the harvester does from these diameter measurements. And this holds true for all of them, that we got a bit closer to zero, although results was a bit varied, with bark being something that is quite dynamic while we're trying to input a certain bark thickness for a certain section of the tree. On the log length side, we actually got some good data out here with differences, average differences for long saw logs being about 1.3 centimeters from the manual measurements. Pulpwood logs was just less than 1 centimeter, as well as the plywood, and then you saw also a better table representing the log length measurements. So the guys talk about the Swedish best five. So the oaks in Scandinavia use this measurement to measure how accurate harvesters are getting their, or how accurate harvester log length measurements are. So they use this plus minus 2 centimeters of what the product needs to be. So for a long saw log, we needed to cut it at 612 centimeters. So this shows that 75% of saw logs cut was within plus minus 2 centimeters of the 612 centimeters. So this range then is from 608 to 612. So it shows fairly accurate length measurements on a harvester head that is calibrated correctly. Overall, it was 86.6, with the shorter logs being more accurate than the longer saw logs. Yeah. So on the volume side of things, again, we took the data, pulled the data from those first 3 plywood logs cut from each tree. So this shows how much more accurate we were in our volume calculations for that section of the stem. So with no bark deduction method, we were missing the mark on volume calculations by about 31% between what the harvester was calculating for that first log and to what the manual log measurements was for that specific log. And this was improved to almost zero for the length-based bark deduction method, and to just over 3.2% for the diameter class length-based bark deduction method. So overall, for that first 3 logs, if you don't use bark deduction method and just use the harvester's over bark measurements, you are overestimating your volume by about 18%. And this was improved to 3.9, and a 3.9 overestimation and then a 2.3 underestimation with the bark deduction methods we used on the harvesters. This just quickly shows the actual stump heights measured in field versus what the harvester thinks stump heights are. So on the harvester's computer, stump height is set at 20 centimeters, whereas in-field measurements showed that the actual stump height was quite a bit lower. And this then obviously influences the harvester's DBH measurement. So if the stump height is set at 20 centimeters, the harvester knows that at that first log at 1.1 meters, that is DBH. And because the stump height, in essence, that the stump height that is actually achieved is lower than the stump out on the harvester's computer, there would be differences in the DBH measurements between what the harvester says and the manual measurements. So in this trial, on those 123's manual DBH measurements was 34.72 compared to the harvester's DBH of 32.82. So just to wrap all of this up, the felling cut has the largest potential for improved underbark diameter measurement with the overestimation of 20.8% for treatment 1 being reduced to an underestimation of only 1.6% and 0.2% for treatment 2 and 3 respectively for that first plywood log. So that's basically for the felling cut. For the first 3 plywood logs, volumes were overestimated by 17.9% for treatment 1, where through the implementation of the bark deduction method, this was improved to an overestimation of 3.9% for trial 2, and then an underestimation of 2.3% for trial 3. The harvester log length measurements compared favorably to international best practice, with 86.6% of the length measurements within the Swedish Best 5 standard. And then there were significant differences between the harvester and manual DBH measurements, which was attributed to a variation in stump height. The diameter length-based bark deduction method is proposed as the best solution, as it was more accurate for the first cut of the plywood logs, and the volume difference for the first 3 plywood logs was also closest to 0. Yeah, I'd just like to thank Professor Pierre Ackerman, Mr. Simon Ackerman, Ms. Kayla Galliardi, and York Timbers for all of the help in putting this study together. Thank you. Any questions?
Excellent. Thanks, Marius.